Herkese merhaba, hoş geldiniz. Bugün 2021 yılının ilk Nano Open'ında Sabancı Üniversitesi doktora sonrası araştırmacısı Dr. Saltuk Hanay'ı konuk ediyoruz. Sayın Hanay ile Sunum ve Hanay İleri Kimya Araştırma Geliştirme ve Mühendislik firması ile ortaklığı olduğu bir startup da söz konusu. Şimdi detayları ve sunumunu yapması için hocam Doktor Saltuk Hanay'a bırakıyorum sözü. Hocam başarılar diliyorum.
Teşekkür ederim Betül Hanım. I will continue in English because I think there is Ali and Ali, Zarab and Ali Fallah. Thanks for the introduction, Betül. Yes, no problem. So I am Saltuk Hanay. Today I'm going to talk about my research that I did in last 8 years. So as you can see, there is some institutes and companies that shows my kind of summary of my CV. But today's topic is about my last 8 years, where I did my work on N-carboxyanhydride polymerization. I started this research in Europe thanks to European-funded Industrial Mercury PhD program, and I finished my PhD and I continued my postdoc in the same with the same professor, and he moved to another university called Royal College of Surgeons. It's a medical college. Then we test our materials in kind of in medical school as well. 2 years ago, I came back to Turkey and I started independent postdoc in Sabancı University. I gave them some proposal and I'm doing research on this proposal. And recently we found a company called Hanay Advanced Chemicals that we are planning to sell N-carboxyanhydride related starting materials and biomaterials as well. And in this company establishment, Sunum helped me a lot in terms of infrastructure and also this paperwork, especially Mert Bey and Gamzan'ım gave lots of efforts to establish my company. I would like to thank them, and also Fazilet Hoca as well. And I would like to thank TÜBİTAK 1512 program for their financial support. So I want to start my presentation with, as you can see, the title is synthesis of protein like macromolecules via N-carboxyanhydride polymerization, which is the technique that I mastered in last 8 years, and their real life application. So I want to start my presentation with protein-like. So in order to understand what is protein-like, we have to refresh our memories what is protein. So if you ask the polymer chemists what's protein, it's a very complicated macromolecule because the polymer is made of amino acids with a known and defined sequence of amino acids. So all amino acids are, their places are known. It's not randomly distributed over protein. And proteins can be between 11 to 34,000 amino acids long. But in general, they are like 300, 400 repeating unit proteins are, I think, very well known. For example, green fluorescent protein is 250 repeating, around 250 repeating units amino acid protein. And they have different functions, as they can be enzymes, they can transport, for example, oxygen like hemoglobin, and they can be used as a structure material in your body like collagen. So how protein is synthesized is actually very complex procedure compared to our chemical synthesis, because you need code for the sequence of the information. So which amino acid comes where is given, this information is given by DNA and transferred to ribosome by mRNA, and this code is reads in ribosome, and tRNA brings the amino acid according to this code, and ribosome also catalyzes this protein reaction. It's a very complicated synthesis. You can do this synthesis outside of cell, but neither with cell or without cell. This process is not like really scalable, and you cannot easily change the protein structure with this method. So chemists come up with different strategies that we can do in our lab reactors, how we can do it. They think about that, and Merrifield in 1963 come up with some method called solid phase peptide synthesis, where you attach amino acids one by one to each other, and you get your polypeptide, and he also got Nobel Prize for this work. And short, I will summarize this method. So you have a solid resin which is insoluble. You attach your first amino acid to this resin, which your amine group is protected. Then you cleave this amine part, and then you purify it, wash it, and you attach another amino acid where the amine group is again protected. So one by one you are attaching amino acid to each other and making a polypeptide chain. But at least 2 steps required for adding one amino acid, and synthesis, even one synthetic step is very tedious process, to be honest. And also you have the purification step. At the end you can able to make peptides, but in theory you can maximum make kind of 50 amino acid long peptides with very low yields. Especially every time you attach amino acid, it's getting harder and harder. So this is not scalable process for long polypeptides, and this is very tedious and expensive synthesis compared to our chemical synthesis that we are making in our lab. And there is also automated systems available, but still these peptides are very expensive, but they are very suitable for pharma and biotech industry where cost is not that important at all. So there is another method, a different method that produces polypeptides, long polypeptides called N-carboxyanhydride polymerization. In this method, this is more polymerization type method rather than adding amino acids to each other one by one. So you start with amino acids. You can take your amino acid, convert it to a monomer called NCA monomer. Then you polymerize these monomers and deprotect. So there is actually you need 2 steps for making long polypeptides. This is a very good polymerization. You get quantitative yields and low dispersity compared to traditional polymerization methods. And this is catalyst free, and byproduct is only carbon dioxide. So you don't really need a purification step for these polymers. You can make large scale polypeptides with this method, and the polymerization is quite fast. And you can make up to 400 amino acids. Yeah, like the reported one is 400 amino acids long in literature, the longest one. The only drawback, of course, not every system is ideal. All system has some drawbacks. The drawback of the system, we don't have a control over sequence, because as you remember, controlling sequence is very extremely complicated process. So you need information and you need catalysts and like some like tRNA type molecules to bring the amino acids according to the code. So it's a very complicated sequence. But we can make different macromolecular architecture. So we can make one block of same amino acid, and we can change the second block with different amino acid. So we have some advantages as well in terms of macromolecular architecture compared to proteins. So if you look at the monomers closely, so this N-carboxyanhydride polymerization requires monomers. It consists of 3 parts. The first part is called NCA ring, where you convert amine and carboxylic acid group of amino acid into this ring, and the polymerization occurs here. And you have the side chain of the amino acids, where your amino acid functionality is present. And most of the time you have to protect this amino acid functionalities, otherwise they interfere with the polymerization step. And once you polymerize, then you have to remove these protection groups to obtain your natural amino acid group. For example, this one is called lysine ZNCA. But once you remove this protection group, you get a lysine, which is a natural amino acid, or in this case, you have the tyrosine. And is it important to make materials from polypeptides, synthetic polypeptides or proteins? It's indeed very important, especially in this age, because nowadays we want materials which are biocompatible, biodegradable, and you could able to control these properties in terms of synthetically. And if you look at the traditional polymers, they are fossil oil based, they are non-degradable. Even the widely advertised PLA is biodegradable, but it's estimated that polylactic acid will degrade in nature 400 to 500 years, and everybody is using in 3D printing. You may know this PLA filaments. There is an industrial industrial degradation process, but it requires heat, and it also releases toxic chemicals as well. Most of the there is a misunderstanding with traditional polymers. Some of them are inert, but people think they are biocompatible, but inert doesn't really mean biocompatible at all, because over time they may become non-inert and they may react with living tissues or bodies. And there's another big important drawback of traditional polymers. They have very limited functional groups. For example, polyethylene glycol doesn't have any functional groups. They have alcohol group at the end. Then you can functionalize. But if you think about proteins or polypeptides, you have lots of available functional groups. For example, you can obtain amine functional group by using lysine amino acid. You can have carboxylic acid functional group using glutamic acid, and it goes on. Like you can add phenol, indole, or thiol, or alcohol group as well. But why people are still using traditional polymers? Because they are cheap and they are readily available. you can easily access to these polymers and you can do research on them. So this, I think, the main reason. Synthetic polypeptides are not that easy. Like they are still scalable compared to proteins and solid phase polypeptide synthesis, solid phase peptide synthesis, but they are not as easy as, in terms of production, they are not as easy as traditional polymers for now. So I want to talk about my PhD project that we obtained some real materials with this method. So we started this again, N-carboxylic anhydride polymerization. Our aim was to use only natural amino acids and make hydrogels out of it. I will talk about hydrogels in next slides, why they are important. So after obtaining polypeptides, we wanted to cross-link our polypeptides in tyrosine amino acid, which is less explored. And if you use this less explored amino acid, you can use other amino acids functionalities for other purposes, like lysine or glutamic acid. Making lysine or glutamic acid free is kind of valuable. So while we were working on tyrosine reaction, which cross-linkers we could use, we found out a compound called triazolindione, and we find a very nice reaction, which we thought is very valuable. So this reaction is called indole triazolindione reaction, or shortly TAD reaction. This reaction is very elegant because it doesn't require any catalyst, heat, UV coupling agent, or it doesn't create byproduct. You simply mix two things and it reacts. So this is a perfect reaction, and at room temperature it happens. But the question is, can we synthesize triazolindione compounds that easy? Sometimes the reaction is very good, looks very good, but it might be very hard to synthesize this compound in your mind. So we check literature if you could synthesize cross-linkers out of this triazolindione, and indeed there are some nice papers published and describing this synthesis very well in large scale. So we followed those papers, and we could able to make library of triazolindione compounds. Some of them are monofunctional, some of them is bifunctional to use as a cross-linker. And as you can see, there is a compound I synthesized like 2-3 years ago. And this compound has distinct pink to red color, and it disappears after reaction. So this TAD reacts with indole very well, but is there an indole containing amino acid in nature? Yes, indeed, and it is thought to be the last amino acid added to protein sequence, which is tryptophan. It contains indole group, and we have one big advantage with tryptophan, because compared to other monomers, as you remember, the other monomers contained protection group, but in tryptophan we didn't need a protection group. So we skip protection step for tryptophan and also deprotection step for tryptophan. So we have a big advantage. Also, we have another big advantage with cross-linking system, because cross-linking doesn't require anything. So it's a perfect system. So it took me like 2-3 months to synthesize tryptophan and say it's not that easy, to be honest, to optimize the condition. But at the end, we could able to optimize the condition and make a large-scale tryptophan NCA. We showed chemical analysis that we are indeed making this NCA in good purity, and we could able to polymerize it. Then we tested our TAD compounds to show it is indeed reacting. And since tryptophan doesn't require protection group, we could able to select other amino acids, whatever we want, and it simplified the synthesis at all. And the TADs are also very stable in this reaction condition. So it's a very perfect system. So you don't have anything to purify, or you don't need to fine-tune any conditions. So it's very elegant system. When things works this well, so you could able to create large-scale materials. So as you can see, we synthesize our tryptophan containing polypeptides, and we cross-link them with our this TAD compounds, and we could able to make large-scale gels. So this is a gel at the first step because it contains a hydrophobic protection group. Remember the protection group that has to be added for the not interfering the polymerization step in the NCA. But once you deprotect the protection step of the protection group of the amino acid, you could able to obtain your hydrogel, because now it turned into hydrophilic group and you could get hydrogel. Also, this work is accepted from the highly competitive polymer conference in 2018, and it's published in top journal in polymer chemistry. So I want to show you how this reaction works. So basically, this big vial contains the polypeptide solution. The other one is TAD compound. As I told you before, it has a characteristic pink to red color. So they are liquid at this stage. So you mix them, and you can pour into a mold. Sorry. And wait until this reaction happens and it turns into a gel. So in this video, it is 20-minute long reaction, but you can make it in 1 minute as well. So basically, you just need to change the solvents. So once reaction happens, the color disappears. Then you have your organogel here. Why is a organogel? I am repeating again because your hydrophilic amino acids are protected. They have to protect it because of the polymerization reaction. But once you dip this gel into acid overnight, these protection groups are removed and you get your hydrogel. And this photo in the gel of the photo is like kind of 15 grams, and I can make kilogram scale in a week starting from amino acid from the first step in a laboratory scale, and I can make like kind of 50, 60 piece of this kind of gels, and the costs are very cheap even if you buy the chemicals from the most expensive vendors like Bachem and Sigma. But is it that's impressive? Because you are in different field and you don't know what is this what does this mean? Like this is something good or bad. In order to understand, you could look at the other work that is published by other researchers. For example, this gel, as you can see on the TV, is published from the top university, one of the top universities, and in top chemistry journal. The level is this actually. In this period, the level of making polypeptide hydrogel is at this level. So our first work is like this. So, but this is very impressive because we can make really large scale and really nice pieces. So this may have commercial value. That's why we also establish our startup company. Because once you are making these things better than anyone else in the world, and you have chance to make out of money of this valuable hydrogels, it's a very challenging task, and we made it simple thanks to tryptophan. It doesn't require protection to protect but also our cross-linking method was very good. But I want to make it some warning here. So polypeptide hydrogels should not be mixed with short peptide gelators like 2 amino acid long peptide gelator FMOC diphenylalanine. Sometimes I talk with people, oh, they say, oh, peptide gel. No, it's not peptide gel, it's a polypeptide gel. The peptide gels are just 2 amino acid long, and they have FMOC group, so it's not a natural group, and they have a very limited composition, so you cannot change. But in our method, we can change. So this is the cross-linking reaction. We can choose any amino acid we want. So this can be lysine, this can be glutamic acid, or this can be serine or thiol-containing cysteine. So we have a very flexible system, and we have a very good working cross-linking as well. And hydrogels are important. If you look at the hydrogels, they are being used in a wide variety of the application areas, and then their global sales are estimated to be 15 to 20 billion euros. We are planning to use our hydrogels in specifically 2 areas: drug delivery and tissue, where you have to send these materials into like living. They have to interact with living organisms. Because our polymers have superior advantage to traditional polymers. So if you make hydrogels out of polypeptides, so they will have a very big advantage in these fields. You can actually make products in all of these fields, but in these fields you have a superior advantage, so we focus on those fields. Then we did some biology studies, cell studies, and we showed that no toxicity observed from surface interaction. These are preliminary studies. And the Young's modules of these gels are kind of in a good range for tissue and engineering applications. And additionally, since this system is very flexible, we can tune the gelation to make porous hydrogels. As you can see in the right photo, it's very porous. This is kind of less porous, and this is non-porous structure. And we are still continuing in Ireland. We are still continuing doing advanced cell studies, and bio applications are also going on. And we will have some papers in coming months as well to show more details about biology and some other properties of these gels. Yeah. So during this gelation step, actually we observed something interesting. As you remember, this at the beginning we get organogel, then we convert into hydrogel by dipping in acid. But we said, what happens if we don't fully deprotect this hydrogel? So this is the scheme. So this is the organogel. You deprotect all of them, you get hydrogel. But if you don't deprotect all of the groups, what happens actually? In our hypothesis was that we could be able to get some material that core is like non-protected, so it is hydrophobic, and the shell is deprotected, so shell is kind of hydrogel. Indeed, we get this material, and we analyze with SEM in water. So you can see this hydrogel part is porous, Actually, both parts are porous since these are gel, but in shell part, this is porous, open pores. This is freeze-dried hydrogel. But in the core, these pores are collapsed on it because they don't like the water, so they collapse on it. So it's a very interesting material. So these are the real photos of this material. So this is kind of cylindrical shape. As you can see, this inside this dye with a hydrophobic dye, outside this hydrogel. So inside this contains the hydrophobic dye, and this is the video of this hydrogel. Since it's a cylindrical, and the core just kind of contradicts, so it forms deformation on the shape. But if you make some perfect spherical, actually you could get perfect core and shell with non-deformed structure. And we also show that we could dye out inside the core hydrophobic layer, and we could also, for example, using rhodamine B, which is hydrophilic dye, we could also just dye or load something into the shell, like without touching the core. And this is also, I think, Reichardt dye with another dye we showed it. And we can also make patterns, and we can selectively make films, and we can selectively convert some of these films, some specific parts of these films into hydrogel. So it was a very interesting work. But for now, this is kind of concept materials. We don't know where we can use these materials, but we are going to use in drug release, but not at this macro scale, but we are going to make these things in micro or even nano scale. So I would like to, in the last part of my presentation, I would like to show some real examples of this our method, N-carboxylic anhydride polymerization methods, and real products of this method. So one of the most known and common product this method is called Glutamar Acetate, which is, as you can see in this structure, it's the random polymers of alanine, 4 amino acids. This is alanine, this is lysine, glutamic acid, and also tyrosine. This polymer is prepared by our method, and Carboxylic anhydride polymerization method. And Weizmann and Teva come up with this polymer to treat as to use as a drug in MS disease. So how it works? Basically, this random polymer is kind of mimicking the myelin basic protein in our body. In MS disease, your immunity system T cells attack your myelin shell, and then they remove it, and this myelin protects the nerve cells, and then you have some nervous nerve disease, let's say MS disease. So what happens is, if you send this polymer into the body, the T cells, this is kind of works as it's not 100% known, this mechanism, but it's thought to be. This T cells prefers to attack this polymers rather than real myelin basic protein. This forms the decay, and your nerve cells are kind of protected. This myelin shell is kind of protected. Patent is expired, but only a few countries produces this polymer, because it's not easy. So you have to produce this polymer, and you have to show that indeed you are making exactly the same polymer in high purity. But this polymer has very less side effects compared to other MS disease treatments. In MS disease, you have to take this medication the rest of your life. So even it has a slight side effect, since you are using this drug rest of your life, it may cause some problems. Other MS medication cause kidney and liver problems, even sometimes psychological problems. But since this is amino acid based and it has a very less side effect, so this is a very valuable drug. And the yearly sales of this drug is approximately $4 to $5 billion in worldwide. And 3 months ago, this Weizmann scientist, I'm not sure if they are the same scientist, but same institute, applied for a patent, showed that this also polymer can be used to treat some of the heart disease. So there may be another drug in future using this protein, this synthetic polypeptide. Another example that polypeptides are used is synthetic polypeptides are used is very different, actually, is in organic chemistry. So this is an epoxidation reaction, but this epoxidation reaction can form two different enantiomers. But if you use poly-L-leucine, leucine is also a natural amino acid. This L indicates the chirality of the amino acid. If you use this specific L containing poly-leucine, you get control over enantiomer, the final product. So basically, it's enantioselectively catalyze the epoxidation reaction. And the studies show that you need minimum 10 amino acid long polyleucine for enantiomer selectivity, and ideal is kind of 30 amino acid long polyleucine. So it's a perfect polymer that should be synthesized by N-carboxyanhydride polymerization, because it's just one amino acid, so sequence is not that important, and you want to make it 30 amino acid long, and you want to make it cheap rather than making some bit expensive. So this is a perfect example for why you should use N-carboxyanhydride polymerization in some cases. And if you use the other enantiomer of leucine, D-enantiomer, which is not natural because nature uses L-enantiomer of the amino acid, you basically get the other opposite enantiomer of this product. And one of the big advantages of NCA polymerization is enables product preparation of LD or LND mixture of polymers, because chirality is preserved during the polymerization. So if you start with L amino acid of the L amino acid, you end up with L polypeptide. So if you start with D amino acid, then you end up with D polypeptide. And you can also control, like if you can make a mixture of L and D. We also have some work in this field. We show different degradation rates for L and D for enzymatic degradation. It will be published soon. And we can look at the other companies that uses this NCA technique and making products. One of them is Star Pharma. It's Australia-based company. So they make polylysine. Lysine is also natural polymer, which is amine. We also showed the structure before. They use polylysine dendrimers as a drug delivery platform. Dendrimer is like a polymer, but it's different. So it's different architecture. So it's kind of tree. So it's lots of branch and lots of side groups, I can say, side chains. And you can make dendrimer types of polypeptides with NCA method. So NCA method is also very strong to make different architectures. So it's one of the biggest advantages of NCA as well. So what they did is this company, they make a polylysine dendrimer as a drug delivery platform, and they increase the efficacy of these known drugs by kind of conjugating these drugs to their platform. So this is, for example, the original drug, taxotere or Gevtine, and they come up with new formulation. Actually, the drug is same, but they put drug into their platform, and these are multi-billion-dollar drugs, and they are working together with the drug pharma companies which produces these original drugs. Another company is A-Microbe. It's a kind of startup company, California-based, UCLA scientists working in there, and they produce synthetic polypeptides that mimics the antimicrobial proteins, such as defenses. As you remember, we give some functions of the proteins. There are even proteins that are antimicrobial. They have antimicrobial functionality. So this company mimics these antimicrobial proteins with synthetic polypeptides. Why it's important? Because if you use antibiotics, nowadays antibiotic research is having some challenging times, because we cannot find new antibiotics, and there are lots of bacteria which gain resistant against antibiotics. But this synthetic polypeptides, in this mechanism, you don't cause antibiotic resistance, and they come up with surgical Johnson solution to prevent bacterial, fungal, and viral infection. They also received a large amount of funding from Carbex. This is a funding body which is dedicated to combat antibiotic resistance bacteria, and this is $600 million fund from Boston University. And it's expected that the next pandemic might be bacteria pandemic. So it's kind of antibiotic resistant bacteria, and then you need novel solutions to kill this bacteria. And in terms of novelty, and if you use synthetic polypeptides, if it kills the bacteria, and if it's biodegradable and biocompatible, so it's kind of extremely valuable material. And there are some companies focused on polymers only rather than direct products, such as Alamanda Polymers and PTS Polypeptides. Alamanda Polymers is US-based, PTS is Spain-based. And they just sell platforms and polymers, and you can use these polymers and you can come up with your own products, such as you can make drug conjugates, you can use as DNA, RNA delivery, and you can use as tissue-targeted drug delivery, such a thing. And Sigma-Aldrich also, or other name, Merck is acquired Sigma-Aldrich. Sigma-Aldrich also sells some polyamino acids. You can buy polyamino acids from there, but these are polymers. It's not a real, like, final product. So you can buy this one and you can apply into your own research. And NCA is also used, NCA monomers, but it's not as a polypeptide, is used as a kind of precursor for drug synthesis. A couple of syntheses shown in these figures. And why it's important, because NCA monomers sometimes enables making synthesis more practical, no coupling agents needed and high yield, so you can use NCA monomers to kind of, rather than making polypeptides, you can make some other small molecule drugs or small molecules for other applications. So Isochem from France also kind of sells some of the NCA monomers. You can check their catalog as well if you're interested. Our company is planning to make and sell monomers and polyamino acids as well. And we are also planning to make MS drug generic version, because in Turkey it's not produced, and in the world is very less produced. Like there's a couple of companies only. But our biggest strength is to making polypeptide hydrogels, which I developed during my PhD, and we have big advantages. And we have some results with antimicrobial properties, and we are planning to also extend this polypeptide hydrogel work in drug delivery and tissue engineering applications. And also we are very interested in siRNA delivery, because we think it will be a very important field in the future. But we will continue with the field which we were in, which we will be more successful. We may just discuss some of the products. So in summary, NCA polymerization is a very good method to produce amino acid-based long polymers. Although these polymers define sequence like proteins, they can mimic some of the proteins like malon basic proteins, or like defensins like a microbe was producing. And different polymeric architectures such as random block, multi-block, or dendritic polymers can be made. For example, Star Pharma in Australia-based company exploiting dendritic architecture to make a drug delivery platform. And one of the most important properties of NCA method is chirality is preserved during polymerization, so enabling an enantioselective catalysis, as I showed before with the epoxidation reaction. And the other one is there is available 20 natural amino acids. They have different function groups. You can also use non-natural amino acids, but I don't want to use non-natural amino acids, because some people are using sarcosine, for example, non-natural amino acid, and they make polymers of it, but it's shown that it may cause some mutagenic reactions. So it's not a good idea to use non-natural product like non-natural amino acids. And they have high biocompatibility and real biodegradability. Is a big advantage compared to traditional polymers. So thank you for listening. And these are like 20 amino acids. As you can see, they have different properties. They can be positive, they can be negative, they can be hydrophilic, hydrophobic. They can have aromatic groups, and they may even have any functional group like glycine. So there is 20 amino acids and unlimited possibilities. It's just your creativity. You can make novel materials, and you can make products. Thank you very much.
Saltuk Hocam, değerli paylaşımlarınız için çok teşekkür ediyoruz.
Ben teşekkür ederim.
Sorular varsa alabiliriz. Katılımcılarımızın sorusu var mı acaba?
Is there any question? You can also send me email if you have a question in future as well. Herhalde yok Betül Hanım.
Evet hocam.
Hı-hı.
Peki, çok teşekkür ediyoruz.
Ben teşekkür ederim.
Nano Open'ımız devam edecek. Duyurularımızı sosyal medyamızdan takip etmenizi rica ediyoruz. Çok teşekkürler herkese.
Ben teşekkür ederim. Oldu. Görüşmek üzere.
Görüşmek üzere.
Thanks. Bye bye. Thanks everyone.
Thank you very much.
Bye bye.
Bye bye.